All right, everybody. How we doing? We doing all right?
Yeah.
Doing all right out there in YouTube world? What did you say? Hey, everybody vote Ian for winter formal. Everybody wrote. Oh, sorry, Ian. I gotta be careful there. There's many Ians. Ian Clevenger.
Yeah.
It's not like I'm denouncing Ian Clevenger. Yeah, and any subsequent years, if you're watching this in like 2021 or 2022, just go ahead and vote Ian Clevenger then too.
Ian and Nathan Moore.
Ian and Nathan Moore.
Let's go.
That's how fast it is with me.
A couple things.
I can't go.
What
Lumineers.
Oh, that's good.
Well,
All right. So the last section out of chapter 6 is what we're going to do today. We will need our graphing calculator, so go ahead and get those out. Curve fitting with polynomial models. Again, we have learned everything that we are going to do today. We've already done this today. Let me remind you that on Canvas in modules, I do have, that's the homework for tonight. Way back, probably here, actually probably in the chapter 5. Yeah, let me see if I put it in there. Yeah, I put the linear regression instructions. Again, that document is the one with all the screenshots on it, the one that looks like this. If you want to go back and print that out again, or if you still have that, that might be a good thing to look off of, because that, now again, that outlines how to do a linear regression, but doing a polynomial regression is like the exact same thing. You just hit a couple different buttons and you're there. So if you want to go back and print that out, I'll probably put it in this module again too. So that's what we're doing today. We're basically taking data. You know, back when we were talking about linear functions, we said, okay, if you get real world data and it ends like this, we can create an equation that models that data, right? Okay. I should turn this around so we can get a better. There we go. Then we said, okay, in quadratics, well, what happens if the data models something like this, right? Well, that would be a quadratic model, right? Okay, so what happens if the data does this? It would look cubic, right? Now, do we see how, right? What would that be? A quartic, and we could keep this process going on and on. Now, I'm not really exactly sure what kind of data would make that shape, but what if we did have that? Well, we could use the correct model to. That's a really good drawing. I'm really sorry out there in YouTube world, you can't see that. We can use our calculators to figure out the equation of this, to model this. Now remember, we had that whole thing with the R value. What did the R value represent? The correlation, the strength of the correlation, right?
You want one.
Yeah, you want 1. The closer to 1, the better. Okay. Now, think about this. The table shows the closing values of the stock index in the first day. Stock index of trading for various years. So stock market, really erratic, right? If you could predict the trend in a stock market, man, you're going to make some big bucks, right? But take a look what we've got here. Closing values of stock on the first day of trading for various years. 774. Okay, look, I go up a lot. I go up a lot more. I go up by 1,000, so it's growing at a very steep rate of change. Up to 4,000, then tanks down to 2,400, then it goes down a little bit more, and then it comes back up. So do you see how this is varying, right? It's kind of waving a little bit. We don't exactly have like some sort of quadratic shape. It's not going up and then back down again consistently. Now it went up, back down, and back up again. So this is an instance where a quadratic model would not be a best fit. Okay, to create a mathematical model for the data, we'll need to determine what type of function is most appropriate. Now, there's a way in your calculator to do that, but there is a way to look at it on a table to see what function is most appropriate, what degree is most appropriate. Now, this is a really simple table here, but so it's pretty kind of self-explanatory. If I've got finite differences, now do we all remember what finite differences are? Finite differences are, if you're looking at a table, you know, say something like this, right? I know I'm jumping to the example here real quick, but if you have, if you're looking at a table, the finite differences are basically just finding the differences in the y values, right? So here, what's the difference there? What do we go up? We go up 6.3, right? Right? And then we go up how much? 4. And then we go up how much? 2.2? Is that right? Check me on that. 2.2? And then 0.9? And then 0.1, right? Now, this is what's called first differences. If these were constant, the function would be linear. If we keep going with that, so that was our first differences, right? If we keep going with that process and find differences within differences, what I mean by that is, okay, what's the difference here? I go down how much? 2.3. What's the difference here? Down 1.8, right? Down what? 1.3? Down 0.8. Okay, if those would have been constant, we would have had a constant set of second differences, and the function would have been quadratic. If it goes down to my third differences and they're constant, then it would be cubic. For example, I'm going up 0.5, 0.5, and 0.5. So I know that this function is going to be not first degree, not second degree, but third degree. We can call this a cubic function. I would know that it would be a cubic function, That's called using finite differences to tell what type of function that you should use. Okay. Now, for our purposes, when we're given a big table of values, we can put them into our calculator and figure out what has the best R value. Which one is going to be the strongest correlation? Okay, which one is going to be the strongest correlation? Okay, so let's do that. Often in real-world data, it can be too irregular for us to use finite differences, or it could be too irregular, or we may not even have enough data to use finite differences, right? Think about where we're going down and down and down and down and down in terms of our numbers of our differences. But what happens if we run out of values? Then we're stuck, right? Then we don't know exactly which ones to use. So it could be too irregular, or you may not have enough data to use finite differences. In those situations, we can use our graphing calculator and talk about the R value, or the R squared value, right? R squared valued is the one that we're going to be looking at, R squared value. So let's get to it. The table below shows the population of a city from 1960 to 2000. Write a polynomial function for the data. Okay, now, on the homework tonight, which I have not written up on the board just quite yet, on the homework tonight, you're going to see there are 3 problems where I ask you to change the input values, where I ask you to change the x values, just like I do in this problem. I say, please let x equal the number of years since 1960. Okay? Let x equal the number of years since 1960. So what does that mean? That means our first x value is going to be what? 0. And then 30 and 40. Okay? The reason we're doing that is because it's going to simplify our equation a little bit. If we don't do that, our numbers are going to get really big. All right. So we go to our graphing calculator. Anybody remember where we go to put in this data? Stat and edit. Oh, looks like I've got some data already there. Remember, you're going to hit clear, not delete up on the top of the list. Clear, not delete. And let's input our data. It's always a really good idea to just double check and see that everything is right. Right, that would stink if you inputted something wrong. I don't want you to lose points just because you're putting something in wrong. All right. Okay, so now what I have to do is find the polynomial function for the data. Okay, I don't know which regression to use yet. So where do I go find my regressions? You go back out to your home screen, and then instead of stat edit, you go stat calc. Now scroll down and look and see what we have. We've got linear. We've done that before. We've got quadratic. Isn't degree of 2 still a polynomial? Right? Isn't that still a polynomial? So quadratic could be the best fit. And then we try cubic. And then we try quartic. Let's see what's down below there. That's just another linear regression. And then we have this thing called ln reg. It's called the natural log reg. Ooh. Yeah, we're not going to get into that just quite yet. But here's what we're going to do. We're going to, whenever it asks you to write a polynomial, I want you to run quadratic. Does anybody have anything more? Does anybody have quintic? I'm always thinking they're probably going to add that in somewhere along the line. Have they added that in yet? No. Okay. We're going to run quadratic, cubic, and quartic and see which one is the best fit. So I'm going to run quadratic. And when you're doing this on your own, you can't really do this screenshot thing. But oops, not a second. But I would always go back and write down what the r squared value was. Okay, hold on just 1 second.
Yeah.
And then 7. Okay, so there's. Notice that on my screen I have to scroll down a little bit. Okay.
That is beautiful.
Oh, it's so pretty.
That around? Exactly. 1.
There you go. All right. Now, if you don't have your r squared values, right, because you need them for this, and I'm glad I'm recording this. If you don't have your r squared values, let me show you what you do. Okay, you go second and then catalog. Right, second catalog, and you got to turn on your diagnostics. So you either scroll down to D, or scroll down to the D's, or hit the D button, and then you have to scroll down to diagnostic on. Come on, there it is. You hit enter on it, it brings it to the home screen, you hit enter on it, and it says done. And now when you run your regressions, you should see your r squared values. Okay, so look at what we have here. These were my 3 regressions that I ran. Which one is the best fit? Quartic. Quartic. Quartic is the best fit. So here's the equation that we write. Here's the equation that we write. Y equals, start way over to the left, 0.0000625. I'm taking it out of scientific notation. 0.00040. 625 x to the 4th plus 0.0996 x to the 3rd minus 2.716. I usually go 3 decimal places out, but I didn't want to just go 3 decimal places out because it would have rounded really funkily. Right, so I that's why I went a little bit more. X squared And then we have x as negative 2 point, oh no, I already did that one. Whoops. We have 108.942x plus 4,267. So that's the polynomial. That's the best fit. That is the best fit for the data. Okay. Now, what can I do with that? Well, let's see. We've got one more. Okay, good. What if I had said, I want to know, based on this model, what it's going to be like in 2020. 2020. Here's what we would do. You go back to your calculator and you go into your y equals. You clear out anything that's there. And you have to turn on your plot, right? You turn on your plot. And you go zoom stat. You turn on your plot and you hit zoom stat. You hit enter. It's interesting that they called this quartic because it looks a little right side of the cube of the quadratic, but whatever. It's not my decision. All right, now from here, I've got to put my actual equation on this graph. Y equals, go back to your y equals, and now I've got to put this equation in. So I'm going to go, now vars, statistics, EQ, and now my regression equation goes in. Hit graph. And it should run exactly through those points. Oh, I see why they called it quartic. It kind of bent a little bit there, didn't it? Okay, now, I said, well, I want to know what happens in 2020, right? Is the year an x value or a y value? An x value, right? An x value. So what I'm going to do is I'm going to go second calculate the value of 2020. No, what? 60. Oh, 60. Why? Because it's number of years since 1960. So I'm going to find the value of 60. Womp womp. What do I need to do? Zoom out. Zoom. Zoom. 3. Enter. And I go second calculate value of 60. Okay, based on this model, in 2020, the population would be 23,345. That make sense? Now, what if I had said, based on this model, when will the population reach, what do we want to say here? 18,000. 18,000. Based on this model, when will the population reach 18,000? Well, is it 18,000? Is the population x value or y value? Okay, so in this case, I've got to go to my y equals and plug in as a y equals 18,000. Let's hit graph and look at that. I see a horizontal line running through my quartic regression. Now, to find where this is going to happen, I have to find the intersection point. So I can calculate intersect, which is choice 5. And then I have to say enter, enter, enter. 53. So in year 53, what year would that be? 2013. Does that make sense? Okay. Should we try to run one more regression? Yeah, that's okay. I'll write the homework up on the board. That's what I'll do. Okay, bye everybody in YouTube world. So long, farewell. Everybody saying goodbye.
Leave a like, comment below. First comment.